Welcome back to Cryptography and Network Security series. In this session, we'll be looking into RSA algorithm. So we'll understand how RSA algorithm works, the encryption and decryption process, what are the fundamental requirements, what are the principles that make it very secure. And we'll also discuss about the computational aspects and we'll see the defense mechanisms and the security aspect. So let's get started. So firstly, we'll understand how RSA algorithm has evolved. Okay, so before RSA, cryptography primarily depended on symmetric key algorithms like DES. So if you have not watched my video on DES algorithm, I would suggest you to watch that and do subscribe to my channel. I'll be uploading videos on the subject, so make sure you don't miss out any of the videos. So yeah, we were speaking about symmetric key algorithms. So before RSA, they were in existent. But these algorithms, they had same key which was used for both encryption and decryption. So there was a challenge, that is how to secure the distribution of the key from both the parties without compromising the secrecy. So that's how public key cryptography. It started from a Diffie-Hellman algorithm, a Diffie-Hellman key exchange. It offered a solution, but it was very limited to just key exchange and did not directly address the encryption and digital signatures aspect. So RSA was invented. RSA stands for Ron Rivest, Adi Shamir, and Leonard Admin. So it was developed by these three on in 1977 at MIT. So it introduced the concept of public key crypto system, where each user will have a public key for encryption and a private key for decryption. So one of the earliest and most widely adopted public key crypto systems enables secure data transmission through the usage of asymmetric keys. We know asymmetric keys will have one public key and the other one is private key. If one public key is used for encryption, then the private key would be used for decryption or vice versa. So it was developed in 1977 by these three scientists. So the RSA derives from their names itself, R, S, and A. Okay, so let's look into how RSA works now. Okay, so firstly we'll look into how RSA key generation happens. So initially we have to choose two large prime numbers. So it could be P and Q. After that we have to find the product of these. N is equal to P into Q. So here N is part of both public key and private keys. Quotient function, which is denoted by phi of n. So phi of n is equal to P minus 1 into Q minus 1. So P minus 1 and Q minus 1 product will give us the Euler's quotient function. So this counts the integers up to n that are relatively prime to n. So we are calculating all these with the respect of n, okay, because n is an integral part of both public key and private key. Next, after this we have to choose the public key, E. Public key is denoted by E. So you have to select E integer such that it lies between 1 and between the Euler's quotient function. So it can be written as GCD of E comma phi of n is equal to 1. So by doing this, this will ensure that E has inverse modulo phi of n. Next, we have to choose the private key here. Private key is denoted by D. Okay, we have to calculate D as modular inverse of E modulo phi of n, which means finding D such that D star E or D into E mod phi of n will be equal to 1. So from the congruent function we are converting into it into the equal to function, and for that we'll be using this particular formula. I've just written down the direct formula. Okay, there is a calculation how these are derived, but then all that is not necessary from exam perspective. So understanding these is sufficient enough. So we'll have the public key which will comprise of the public key and the n value, that is p into q, right? Next, again in private key also we'll get d comma n. D is the private key which we have selected. Okay, now that we are generated with the key, we'll now look into how to get the encryption and decryption formula. So RSA encryption. So to encrypt a message M is the message length. Okay, we have to convert M into a number that is less than n firstly and compute the ciphertext. So C is equal to M power E mod n. So this is the formula. So here the sender will use the receiver's public key E. Okay, sender will send the recipient's public key to perform this encryption. Whereas coming to decryption, so to decrypt ciphertext, we'll be using M is equal to C power D mod N. So here D is the recipient's private key. Okay. So after finding out the RSA encryption and decryption, we'll be able to get the final answer through this. Okay, so these steps are very important. There's a figure also which explains these. We'll look into that further. Now we have requirements and security aspect of RSA. So RSA relies on difficulty of factoring large numbers because we are taking large numbers P and Q. So it becomes very difficult for the cryptanalyst to decode this, or in the process of calculations we have made multiple transpositions and conversions, right? So here it becomes difficult for the cryptanalyst to decrypt it. So the key considerations here will include, first one is infeasibility of determining D. That is, it should be computationally infeasible to determine the private key from the public key E comma N. Next, we have trapdoor one-way function. Trapdoor one-way function. So RSA leverages a trapdoor one-way function where public key makes encryption and encryption easy, but decryption without private key is infeasible. So it's just one way. With public key you can just encrypt it, but then in order to decrypt you will be requiring the private key accordingly. Okay, so these are the two key considerations which are to be kept in mind while dealing with the RSA algorithm. Next, we have the applications of RSA. Encryption and decryption. So RSA algorithm is to encrypt and decrypt. So it will securely transmit the messages by encrypting with the recipient's public key and decrypting with their private key. Then we have digital signatures. Digital signatures are the signed messages with the sender's private key, enabling the recipient to verify the authenticity using sender's public key. Then you have key exchange. So this will establish a shared session keys securely by using RSA in combination with the any symmetric encryption for efficient data transfer to happen on both the ways. So we can say that RSA is widely used in secure communication protocols like SSL, TLS. So this is used for protecting the internet data and remains as one of the fundamental cryptographic algorithms even today. So this was about the requirements and security aspect of RSA. Next, we'll look into the figure here, as I told you. So this figure explains the algorithm. First, key generation by Alice. Okay, so Alice is generating the key here. So firstly select P and Q. P and Q should be both prime such that P is not equal to Q. Then we are calculating N value, yes, P into Q. Then we'll calculate the Euler's quotient function phi of N, which is equal to P minus 1 into Q minus 1. After that we have to select integer E. We have to select integer E such that GCD of phi of N comma E is equal to 1. So after that we'll be calculating D, public key and private key. D is equal to E inverse of mod phi of N. Congruent function is being used here. So that's what, as I explained here, I have written it in very simpler terms. Okay. So after this we'll get the public key and private key. Once these are obtained, I have to perform the encryption by Bob, that is by recipient, with Alice public key. So Alice public key, will be making use of Alice public key here. So M, that is the length of the text, should be lesser than the N value, product of P and Q. Okay, first condition is that. Second will be using this formula. In order to get the cipher text, we'll take length of this M power E mod of N. M power E mod of N will get the cipher text. In order to decrypt, decryption by Alice with Alice public key. So Alice public key we are using to decrypt it. So cipher text C is available. Now in order to get the plain text, M is equal to C power D mod N. So C power D mod N would get us the plain text here. So we look, if we see the algorithm just by this way, we may not be able to understand it. But then let's look into the problems. We have two problems here. So by this it will be clear and easy to understand. So the first example is P is equal to Q, P is equal to 3 and Q is equal to 5, and the text is FROG. Either the text can be given or the length of text can be specified here. Okay, so the first step, I have to calculate N value, right? P, Q are there and P is not equal to Q, again checked. Then I have to calculate N value, that is N is equal to P star Q, 5 into 3, 15 I got, done. After that I have to calculate phi of N. Phi of N is Euler's quotient function, which is equal to P minus 1 into Q minus 1, that is 4. 5 minus 1 is 4 and 3 minus 1 is 2. 4 2s are 8 I've got. Next I have to select the public key. Selecting E, GCD of
E comma phi of n is equal to 1. So we know phi of n is 8. So GCD of E comma 8 have to get 1. So I'll have to substitute values here, trial and error. E is equal to 3, first I'll check, then E is equal to 5, E is equal to 7, and so on. So by substituting the values here, if I take GCD of 3 comma 8, I'll get 1. So that's how I get E is equal to 3. Next, calculation of D. So here D star E mod phi of n is equal to 1. So here again D value is unknown, I have to calculate D. E value is 3. So D star 3 mod 8 is equal to 1. So I have to write something in place of D such that I would get mod 8 is equal to 1. So if I write 3 here, 3 into 3 is 9. 9 mod 8 is equal to 9 is greater than 8. So 9 minus 1, that I get as 1 here as the output. So D is equal to 3 is acceptable. So anytime if we have to calculate E or D, start from 3, 5, 7, 9 and so on. Okay. Next, private key and public key. So I have obtained the value of E and D. Let me write it in these ways. Private key is D comma n, that is 3 comma 15, and public key is also E comma n, that is 3 comma 15. Here private key and public key E values and D values are same, but then it need not be same always. Okay, just in this question it is same. Okay. So after obtaining the keys, we have to perform the encryption and decryption. M value is 4, total length is 4, FROG 4 characters. So I can write decryption M is equal to C power D mod n. So here I'll write 4. The ciphertext which I have obtained is sorry. Here it is C is equal to M power E mod n. So C is the ciphertext which I want. M value is 4. So 4 power 3 mod 15. 4 power 3 is 64. 64 mod 15 is, I get it as 4. So 4 is the ciphertext which I have obtained. Next, I have to do the decryption. So for decryption, I have to get the plain text, right? M is equal to C power D mod n. So it is 4 power 3 mod 15. 4 power 3 is 64. 64 mod 15 is 4. So that's how I have obtained the plain text also. So before encryption also the length of plain text was 4, and after encryption and decryption the length of plain text is 4. So this means our conversion or the data transfer has happened securely or successfully. So this was about the first question. Let's look into one more question here. So we have P is equal to 17 and Q is equal to 11, M is equal to 88. So these are slightly larger prime numbers compared to the previous question. So prime numbers is equal to P is equal to 17 and Q is equal to 17. We have to check whether P is not equal to Q. Yes, this is correct. Then we have to calculate N. N is equal to product of P and Q, 17 into 11. 17 into 11, I get 187. Next, I have to calculate the Euler's totient function, which is phi of n, which is equal to P minus 1. P was 14 here, so P was 17 here, so 16 into Q. Q is 11, so it is 10 here. 16 into 10 is 160. I got Euler's totient as 160. Next, I have to calculate the public key. Public key is equal to GCD of E comma phi of n is equal to 1. So here GCD of E comma 160 should be equal to 1. Now I'll check substituting 3 here, 5 here and 7 here. So when I substitute 7, I get GCD of 7 and 160 as 1. So thereby this 7 is fitting properly. So again trial and error, start from E is equal to 3, 5, 7, 9, 11, 13 and so on. Okay, so E is 7 here. Next I'll have to calculate the private key. So D star E mod phi n is equal to 1. So D again 3, 5, 7, 9. So D star 7 mod 160 is equal to 1. So if I substitute 23 into 7 mod 160, I will get 161 mod 160, which is equal to 1. So there D is equal to 23 is the perfect number which I can fit here. Okay, so I have obtained my keys. So the first one was E is equal to 7 and D is equal to 7. Let me write down them in this format. So public key is equal to PU E of E comma N. So E is 7 and N is 187. And private key D comma N, D is 23 and 187 I have written. Now that I have obtained the public key and private key, I have to look into calculation of or performing the encryption and decryption process. So for encryption, I take, in order to get the ciphertext, I'll be taking the length of the plain text up to the root E. E here is the public key mod N. So here m is 88 power 7 mod 187. So if I solve this, I would get 11. So I've got 11 as the cipher text. Okay, next I have to do the decryption. In order to get the plain text, I have to take cipher text to the power private key and mod of n. 11 power 23 mod of 187. The answer would be 88. So before encryption also, before encryption also the plain text length was 88, and after encryption and decryption also the length is 88. This means that our transfer of the message or communication has been securely completed. So this was about the second example. This example was there in the textbook, and it could be asked in exams also. So yeah, so here again the figure explains everything. So yes, it's the same. Encryption is done, plain text is here, and here I have the public key, and here I have mod 187. 187 is the value of n. I get 11. 11 is transported, and here 11 power 23. 11 power 23, because 23 is the private key, and mod 187. 187 is the n value. I get the plain text back. Here plain text was 88, and here also plain text is 88. Now let's look into the computational aspects of RSA algorithm. So the complexity involved in RSA can be broken down into two main tasks. First, now we'll look into encryption and decryption. So encryption and decryption of RSA algorithm will depend upon the modular exponential operation, especially raising an integer to an integer power modulo n. Raising an integer to an integer means, here if you see, firstly we have taken the plain text to the power an integer public key, and here also we have taken the ciphertext to the power integer and then performing mod again with an integer. So this integer is p into q, right? So the entire complexity or computation depends on this particular modular exponential operation. Then we have modulo arithmetic, that is a mod n into b mod n multiplied by mod n would give a into b mod n. So this means that we can deduce or reduce the intermediate results modulo n, making computations feasible despite potentially large exponents. Next we have is efficient exponentiation. So in efficient exponentiation, we have two options: either the standard or the straightforward approach, that is x power 16 means we have to perform 16 times multiplication, or we have the optimized approach. In optimized approach, instead of performing 16 multiplications, you are writing the exponential form to subdivided exponential form, that is 8 power x to the power 2, or if it is 8 power 8, then it is x power 4 to power 2. By using this method, it will reduce the number of multiplications very significantly. Okay, so this was about the first computational aspect. Second we have is the key generation. So it involves generating two large prime numbers, deriving the public key and private key. The selection of prime numbers must be to prevent factorization attacks. So we have to select the prime numbers distinctively, p and q, and n value also it has to be unique, and yeah, the numbers which we are selecting should be very random, and we have to apply a probabilistic primary test, that is to determine whether a number is likely prime. So the more tests a number passes with different random bases, the higher would be its confidentiality that it is prime number. Speaking about the efficient operation, public key efficiency. Public key efficiency, in order to enhance the performance, will be making use or selecting the choices E in this range 3, 17 and so on, which will minimize the number of multiplications during encryption process. Then private key. So calculating m is equal to c power d mod n can be speeden up, or we can increase the speed by using the Chinese remainder theorem CRT, which allows for computations modulo p and q separate. So and then we combine the results here. So this algorithm or this theorem is not that important from exam perspective. So next we have is the security aspect of RSA algorithm. So security aspect, in first we have types of attacks here. So there are 5 different types of attacks mentioned in the textbook. We'll look into one by one. Okay. So although RSA algorithm is widely used public key cryptography, but then it has several potential threats. So each of these threats will have a particular defense. So firstly we'll see what are the threats, and then we'll speak about the defense mechanisms. Okay. So the first threat which we have is brute force attack. So brute force attack will involve attempting all possible private keys to decrypt the message. So the effectiveness of this method is just limited to the key size, because if the key size is very large, then it becomes difficult for the attacker to keep on checking it again and again and again, right? Next we have is the mathematical attack. So these attacks will involve around factoring the product of two large numbers, that is p and q. So common strategies could include like factor n into two prime numbers p and q, and then we'll determine the totient function, that is f of n is equal to p minus 1 q minus 1, directly without finding the p and q value, and then we'll compute the d value, that is private exponent, directly from e and n. So the challenge of factoring large numbers is a drawback. The challenge of factoring large numbers is one of the security aspects of RSA security. As the computational power increases and the factoring algorithm improves, the effective key size needed for security also increases drastically. Then we have is the timing attacks. So these will exploit the variations in the time. So the time which is taken to perform the cryptographic operations. So if attacker can measure how much time is being taken or how long does it take to decrypt different ciphertext, then he can get some bits of the private key. So the countermeasures for this is to ensure that there is constant time operation for any modular exponential operations which we are performing, and then introducing random delays to confuse the timing analysis, and then use binding techniques to obscure and hide the actual ciphertext which is being processed. Then we have is the hardware fault attacks. So this method involving faults in the hardware, that is by manipulating the power supply during RSA operations to generate incorrect outputs or any other such operation. While this requires physical access to the device, it speaks about the vulnerability of hardware implementations. Then we have chosen ciphertext attack. So in this attack, the attacker can choose arbitrary ciphertext to be decrypted and gain the insights from the resulting plain text. So the basic RSA algorithm is vulnerable to such attacks. So the implementation of secure padding schemes like optimal asymmetric encryption padding can safeguard or prevent from such vulnerabilities. So this was all about the security aspects or the types of attacks. Let's look into the defense mechanisms. First one is to use a large key size. So a large key size increases the complexity of brute force and mathematical attacks. We know this. Then we have mathematical constraints. So while generating the prime numbers p and q, we have to ensure that they are of similar length, and both p minus 1 and q minus 1 also should be large prime factors. And then the greatest common divisor GCD of p minus 1 q minus 1 should be very small. That's why we have taken GCD as 1, right? Next, we have implementation considerations. That is, while employing the constant time algorithms, we can prevent any timing attacks. So along with that, we have to implement the binding techniques also. Yes, we have discussed this. Then we have regular security audits. So continuous assessment of the cryptographic environment will help us to identify and rectify if there are any vulnerabilities. So these vulnerabilities are, if they are very posing a great threat, then they need to be addressed then and there. Okay. Next we have is secure padding schemes. So implementing the secure padding schemes will help us to overcome the risks which are associated with choosing a particular ciphertext and deducing the plain text. So we can ensure that ciphertexts are transformed in a secure manner before decryption happens. So finally we can conclude that RSA will remain one of the highly used techniques even if the new methods are emerging. Okay, so by utilizing the large key sizes, implementing mathematical and operational constraints, we can make sure that the security or the risks are mitigated. So this was all about RSA algorithm. If you have any doubts, do let me know in the comments, and subscribe to my channel.